Hi, my name is Ian, and we're going to be dealing with numbers and number patterns. Now, in your textbook, numbers are found on page 1 through 13. Let's get started. Well, the key focus of this is investigating number patterns. This is the second part that we're going to be doing, is number patterns, and specifically where we have linear number patterns. We're going to be looking for the general term, we're looking for a specific term, but we're looking for linear. Now I'm going to touch on a couple of other things, Fibonacci series, a couple of really funny series, maybe a second difference pattern, but essentially in grade 10, where we are at the moment, it's going to be linear patterns. That's the one thing I'm going to be doing. The other thing I'm going to be doing is talking about the difference between rational numbers and irrational numbers. Okay, and I'm also going to be looking at where surds lie on the number line. A surd, something like the square root of 2, where does that lie on the number line? Between which two integers does it lie? So we're going to have to revise what are whole numbers, what are integers, so that we can find out where these irrational numbers lie on our number line. Also, touching on briefly, accuracy, rounding off accuracy. I know that a lot of you did that in primary school. We're just going to touch on that. So, let's have a look at the number system. Now, the number system that we're going to use at school is the real number system. Consists of that number line. Let's call the middle 0, and we've got the positive numbers, positive 1, positive 2, positive 3 going up, and the negatives, negative 1, negative 2, negative 3, negative 4. Let's just have a look at the diagram and we can talk about the different kinds of numbers we get. Now in the middle we get the natural numbers, and that's what I was talking about, the natural numbers. Things like 1, 2, 3. Some people will say that's where counting started. As the sheep came out of the kraal, you said 1 sheep, 2, 3, 4. And eventually people decided there were no sheep, so they had to have a symbol for 0. And they got the little round circle, the little naught, and they called those the whole numbers. So what we've got is we've got the natural numbers together with the element 0 make up our whole numbers. And there we can see the little 0 under the N. Now, it often gets rather cold, and how do you distinguish between 15, 16, which is still a little bit chilly on a nice day, and -3, -4, and those poor people who live in Sutherland down in the Cape where it gets to -10, how do you distinguish that with a number? So we decided to use negatives. And the negatives, together with our whole numbers, came together to make the integers. Let's have a look at the diagram. There are our integers. Now the integers are the whole numbers combined with the negatives. So if I have a look at a number line with 0 over there, 1, 2, 3, etc., -1, -2, -3, etc., those are the integers. Now, this is more for girls than for boys. Boys, when you have a pizza or a hamburger or a cool drink, you don't share it. So you don't have to really worry about fractions. It's the girls who like to be sharing things. And we have to distinguish between integers and fractions. So they decided any rational number would be one integer over another integer, like 5 over 6, or 1 over 2, or minus 3 over 7. And those fractions, together with our integers, make up our rational numbers. So back to the diagram. So here we go. Our rational numbers are our integers together with our fractions. Now, you can see on the diagram over here, there's something called irrational numbers. And I'm going to scroll down on the screen a little bit and put a definition. Our irrational numbers are non-terminating, which means they never end. It's like the Terminator. I'll be back. Irrational numbers never end. They also are non-recurring. And they are decimals. So an irrational number is a non-recurring, non-terminating decimal. Now you heard the story about a guy going into a pub. And he was told never speak to that man in the corner because he just goes on forever and ever and ever. And his name is Mr. Pie. I hope you got that. It was a joke. Examples of irrationals are the number pi, the number like square root of 2, a number, for example, like the negative cube root of 7. In fact, there are an infinite number of irrational numbers and also an infinite number of rational numbers. So, what have we got? We've got your irrational, non-terminating, non-recurring decimals, and we've got your rational numbers, any number that can be written as a fraction, one integer over another. Numbers like a half, 5, negative 6. And when we put them together, we get the real number system. Let's go back to our diagram and have a look at that. There we go. We have the rationals and the irrationals, and together they make the real number system. A real number is any number that you could place somewhere on your number line. So on our very roughly drawn diagram over here of a number line, I could say that a half is somewhere over there. I could say that the square root of 2. Now, let's just double check. What is the square root of 2? Comes up as root 2. So I press the surd to decimal button, S to D button. It's 1,412, etc. Let's go back to our page. 1,4, somewhere, oh my goodness, that shifted. Somewhere over there, I could find the square root over 2. Now, I know that we can't place it exactly on a number line because we don't know what its last decimal place is because it hasn't got one. But we know approximately where it is. That's one of the things that we're going to be talking about a little later. So, rationals, irrationals together make up our reals. I'm sure you've got it. Let's move on. Now, what we need to be able to do is to show that recurring decimals actually can be written as fractions. So a number like 0,33333, which is written as 0,3 with a little dot on top of it, is actually a rational number because we can write it as a fraction. Remember, anything that can be written as a fraction is rational. So let's run through this explanation over here. Well, we've got 0,3 recurring, and that little symbol on top shows us that it's recurring. Sometimes people might use the notation 0,3 with a little bar on top. It means exactly the same kind of thing. And here they're saying we need to write it as a fraction. So let's run through a sophisticated explanation. Now this is sophisticated. I'm going to give you a little trick as well as show you how to do it on the calculator, but this way works for everyone. Please find out from your teacher what he or she would really like you to do in a test, whether it's answer only or actually to prove that a recurring decimal can be written as a fraction. So that's up to you to do. Let's have a look at this example. First of all, we define x as 0,33333 recurring. That was step 1. Step 2, we're going to multiply by 10 on both sides. Now remember, it's an equation. We've let x be 0,3 recurring, so 10x will be 3,33333. That's step 2. And step 3, we are going to subtract the first equation from the second. So I'm going to just write it over here. 10x is equal to 3,333 recurring. X is equal to 0,333 recurring. And what I get from my subtraction is that 9x is equal to 3. Well, if 9x is equal to 3, x must be equal to a third. My goodness, we've done it. We have shown that 0,3 recurring is a fraction. It is a rational number. Now, here's a little trick. I'm going to show you a couple of examples, and you can try them out on your own. 0,4 recurring. It's one decimal that's recurring. There's no funny stuff in front of it. It's just a recurring decimal. That's going to be 4/9. If I have 0,5, and I'm going to just rub that bit out. If I have 0,56 recurring, there you can see I'm using a different notation. That's 56/99. Two figures that recur over 99. How about if 3 figures recur? Ah, you got it. That's right. Thank you. For example, 0,123 recurring would be 123/999. Now you can all see that that doesn't require any sophisticated working. It just requires the trick, the knowledge. What I'm going to show you now is how to do it on your calculator. Very quickly, and later on I'm going to do a whole lot of examples with the complex method, as well as easily. So this is just to whet your appetite. I'm going to bring up my calculator. Now remember, the calculator works to about 13 decimal places. So you've got to overload it so that it doesn't see it as a number, it sees it as a recurring decimal. Have a look. 0,4444 recurring is 4/9. That's almost magic, isn't it? All we got to do is hit the equal sign. Now, what you're going to see is perhaps the fraction can simplify. I don't know, some of you probably are shouting saying, I didn't simplify that 123/999. I know I didn't. I was just showing you a trick how to write as a fraction. We'll worry about the simplification in a few minutes. Let's do the second one. Well, that's 0,56 recurring. So it's 5656 repeated. And there we go. 56/99. Isn't that amazing? Absolutely fantastic. The calculator can do this for you. So, let's do the last one. And remember, it was 123 recurring. So 0,123. and hit it. 41 over 333. And yes, that over there is 41 over 333. So what happened there? The calculator actually simplified it for you as well. So, just to summarize, we've done a very sophisticated method. We've done a little trick. If there are no funny bits hanging around, it's only the recurring bit. And I've showed you how to use the calculator to do it. Now, if you're required to prove that something is a rational number, you're going to have to use the sophisticated method. And you can always check your answer with the calculator. Let's move on. Here we come up with something which is slightly trickier. So what we're going to do is we're going to use the sophisticated method, and then we're going to show you a couple ways to check your answer using the calculator. So step one, just as we did last time, we define the equation. Now, how many decimals are recurring? It's 3. So step 2 is we're going to multiply 1 with 3 zeros, 1,000. And there it is. 1,000x is equal to this over here. And just as happened before, we are now going to do step 3, which is to subtract one equation from the other. I'm going to write this up over here, just so that you're all happy with it. And I want to show you something quite fantastic. 5432, and then we have our 5432 recurring. Over here, where x was 5,432 recurring. Now, when we subtract, what I want you to have a look at is the bit that recurs. Because it's exactly the same all the way to infinity, it'll subtract. And that's why we chose 1,000. So that our 432 on the right-hand side of our decimal place would be exactly lined up with the other 432. So it can subtract. So over here, all these 432s disappear. And what I'm left with when I subtract is, and here we go, 999x is equal to 999x is equal to 5427. And the reason why we do the sophisticated way is to get rid of that decimal place. All those decimal places disappear, like the morning mist when the sun rises. So, last step, simplify. And in this case, we can simplify our denominator. The 999 goes down to 37. Now, I would be quite happy in my class if you gave me 201 over 37. Quite happy. You have shown that this number can be written as two integers over each other. Some people prefer the mixed fraction, in other words, the integral part and then the fraction part as a proper fraction. Please find out from your teacher which they prefer. I just enjoy the top-heavy fractions. Now, I said to you I'd show you another way to do this. Have a look here. I've got 5,427, and the 427 is the bit that is recurring. I can write that as 5 plus 0,427, with the 427 that the bit is recurring. Now, we know that that is 5 plus 427 over 999, which is 5 plus 16 over 37. How about that? Just another way to do it. And yes, if you pulled up the calculator and you punched it in, you punched in more than 13 repetitive digits, Yes, the calculator would come up with 201 over 37. Amazing, isn't it? Right, let's move on. The next explanation I'm going to go into is a thing called estimating surds. Now remember, what is a surd? A surd is something under a square root or something under a cube root, something that is an element of the irrationals. You heard the story about the man whose wife was very upset with him. He said that she was irrational. She just kept going on and on at him. Anyway. Right. Here's a question. Find two consecutive integers such that 26 lies between them. And here's a little explanation about what the word consecutive means. Now, consecutive just means one after the other. So consecutive numbers would be 1, 2, 3, 21, 22, 23. Consecutive odd numbers, 7, 9, 11. Consecutive even numbers, 14, 16, 18. Just numbers that are consecutive, one after each other. So, we've got to find 26. Where does root 26 lie? What we're going to use is we are going to be using perfect squares. Now, just to remind you, perfect squares 1, 4, 9, 16, 25, 36, etc. Those are perfect squares. We're going to use perfect squares to estimate the lower integer. Well, we know that 25 is 5 squared. So the square root of 25 is 5. But we're looking for the square root of 26. So 5 must be just a smidgen, just a tiny little bit smaller than root 26. And let's have a look at the next one. Well, here we have it. 6 squared is 36. So 26 is slightly less than 6. So what can we say is that root 26 lies between 5 and 6. So what do you need to know here? You need to know your perfect squares. 1, 4, 9, 16, 25, 36. And how about if we had a cube root? You need to know your cubes. 1, 2 squared, 2 cubed, 8, 3 cubed, 27, etc. Perhaps it might be a good idea for you to make a list. Stick it on your bedroom wall. Have a read through every evening. Within a couple of days, you'll have it memorized. How about using the calculator to answer this question? Let's have a look at the calculator. If I have the square root of 26, it says root 26. So what do we have to do? Surd to decimal button. 5,099. What does that mean? It means root 26 is just bigger than 5 and quite a bit smaller than 6. But it lies between 5 and 6. So on our number line, let's go back to our page. On our number line, if we had 5 and we had 6, somewhere over there, we'd be able to put root 26. Somewhere between 5 and 6. Let's have a look for cube root of 49. Ha! We knew it would come, didn't we? Here we go. Now, let's have a look at the calculator to run up a table of cubes. Isn't that exciting? A table of cubes. Let's have a look at the calculator. I'm going to go to table mode, option 3. And I'm going to ask for x to the power of 3. Just for those who might have missed it, x is in red, so we have to press the alpha first. So alpha x, and then I wanted to raise it to the power 3. I'm going to start at 1 and end at 5. Why not? Steps of 1, and there we go. On our right-hand side, 1, 8, 27. Let's move down. 64, 125. There we have a table of cubes. You could run a table of cubes to anything. I'm not sure what the limitations on memory on your calculator are, but obviously you could do it in start at 10 and end at 20 and do sets of 10. Perhaps you don't want to end at cubes. Perhaps you're one of the really, really bright kids. You want to learn to your power 4 and power 5. There's a challenge. Let's go back to the question. Right, here we go. Cube root of 49. Well, perfect cubes, to estimate the lower integer, we've got the 3 cubed is 27. So it is slightly bigger than 3 and slightly smaller than 4. And there we can write the answer. What were our cubes again? 1, 8, 27. Let's go back to our calculator to get them. 64, 125. 64, 125. So we can quite easily see that 49 fits in over there somewhere. So it lies between 3 and 4. Somewhere on the number line between 3 and 4, you'll find the cube root of 49. And yes, we can also check this on our calculator. And there is a cube root button on our calculator. Let's go back to computational mode. And hiding over there on shift is our cube root. So cube root of 49 is, well, just over halfway between 3 and 4. True statement. So somewhere between 3 and 4, there lies cube root of 49. Okay, what we're going to do now is we're going to take a 5-minute break, or a few minutes of a break, and when we come back, we're going to be doing a whole lot of examples out of your textbook. I hope you had a good stretch of the legs, and maybe a slight debate about who was going to learn perfect cubes. Anyway, I'm going to be doing a bunch of exercises now from page 39 onwards in your textbook. Things that could come up in tests, in assessments, and spend a little bit of time talking through them. Here we go. The first one is on numbers. And they talk about if A is an integer, and B is an integer, and C is irrational. So what I'm going to do is I'm going to remind ourselves that C is irrational. Okay, let's have a look. Minus B over A. That means I've got an integer over an integer. Now, what is that going to give me? Now, if we go back to our definition of a rational number, what was the definition? An integer over an integer. Now, what this question is asking is, are these numbers going to be rational or irrational? So let's have a look. Here we've got an integer over an integer. So in this case, the answer, it is going to be rational. Now, have a look at B. I know that C is irrational, but C divided by C, isn't that 1? And 1 we know is an element of the rational numbers. So there we go. Another rational number. Okay, you see how important it is to know what a rational number is and to know that what might seem laborious definition. Quite important. Let's carry on. Question C. Here we have an integer over an irrational number. For example, 3 divided by root 2. Now, you might like to try 1 or 2 examples on the calculator just to double check yourself. So I'm going to do 3 divided by root 2. Let's go over to the calculator. Hit my fraction button. I've got 3, and it's going to be over root 2. And goodness me, what is that funny monster that's popped up there? That's an irrational number. It's written in surd form. The calculator can't simplify it. Neither can I. That definitely is irrational. So C, an integer over an irrational, is irrational. So this one is an element of the irrationals. It's not rational. Likewise, our last little number is also going to be an element of the irrationals. Everyone happy with that? Right, let's move on. Here we go back to writing decimals as simple fractions. Now remember, if they recur, they're over 9 or 99 or 999, or we might have to do the sophisticated way. But what we're going to be able to do in the first couple is just rely on our knowledge from grade 8 and grade 9. Let's have a look. 0,12. Well, that's equal to 12 over 100. No recurring, no problem. Now, sometimes people get a little bit mixed up, and they're not quite sure 12 over 100, well, what goes into 12 and 100? Well, we all know that 2 goes into 12 and 100. So we could write that as 6 over 50, but 2 also goes into 6. Some people might find that too tedious. So let's double check it on our calculator, and then we can also do it again. So here on our calculator, we have 12 over 100, and that gives us 3 over 25. Now I know that there are lots of you out there that see 12 over 100 and just think 3 over 25. You know what it is. I know that you're out there. But there are some kids who struggle, really struggle with numbers. Do you remember why it simplifies down to that? Let's have a look at this. Well, we know that 12 over 100 can be written as 4 times 3, and 100 can be written as 4 times 25. Okay, so what would happen here is we can now write this as 4 over 4 times 3 over 25, which is 1 times 3 over 25, which we know is 3 over 25. Now, I know that you know how it works. But just in case, for those of you who weren't quite sure, that is how it simplifies. I know some of you might like to use the word cancel. The real technically correct word is simplify. And that's what we've done. We've made this 12 over 100 look different. We've simplified it and made it as 3 over 25. Let's move on. 0,006 is 6 over 1,000. Yes, 6 over 1,000 can be simplified. Just in case we're not sure, let's go 6 over 1,000, and that gives us 3 over 500. Now here's something that's slightly more different. I'm going to do it 2 different ways. See which way you prefer. I could say that is 159 over 100. And then I can simplify it from there. Well, actually 159 over 100 can't be simplified. The other way to do it is to split it up into the integral part and the fraction part, like I'm going to do here. I could write that as 1 plus 59 over 100, which we all know is 1 and 59 over 100. And that might be a little bit easier for you to break the integral part and to break the fraction part, to separate the two. Might be easier. Right, here we go. D. D, a little nasty one. Well, here we have 12,277 recurring. I'm going to cross that little bit out, and I'm going to put the recurring sign there, because that's exactly what it means. So I'm going to say, let x be equal to 12,27 recurring. And whatever I do, I've got to find x. So whatever I multiply by, I've got to find it. Now, you'll notice here, there's a little something and then the recurring bits start. I want to shift this all up so that only the recurring bits are on the right-hand side of the decimal comma. Have a look here. If I say 100x, that'll be 1227, 7777, etc. And if I said 10x, that would be 122, 777. I'm sure you know why I've done that. It's so that on the right-hand side of the decimal comma, all those recurring bits line up. And when we subtract, they disappear. Poof, gone like magic. So here we go. We are going to subtract, and I get 90x is equal to, and all these decimal commas over here all disappear. And 7 minus 2 gives me 5, and I get 1105. Simplifying, x is equal to 1105 over 90. And if I simplify that, like the good pupils, you will also simplify, I get 221 over 18. Oops, let's extend the page so I can get the 18 in there. So, let's track back slightly. Change ink. The first thing was, define my equation. Let x be 12,27. That's what they're asking for. Let x be what we're trying to find. Then we've got to be careful in our selection. We want only the decimal commas on the right-hand side. Only the recurring things on the right-hand side of the decimal comma. So in this case, because they're 2, I'm going to multiply first by 100 and then by 10. So that all this over here, all those 7s, all the way down to infinity, disappear. Our last little step is to divide through and simplify. Now, when you try this at home, or with your mates, or in class, if you're not quite sure if you got the right answer, yes, you can use the calculator. Let me show you how to do it like that. Bring up our calculator, and we've got 12,2777777, and I've just got to overclock it a little bit and pop in the equal sign. There we go, 221 over 18. Now, for those of you who prefer to write it as a mixed fraction, in other words, an integral part and a fraction part, not a top-heavy fraction, all you need to do is to pop the calculator again. There we go. It gives it to you that, like that, or if you go shift and that's third to decimal, it splits it up, 12 and 5/18. Quite magic. Gives it to you, or shift, and that again splits it up for you. I hope you've all got that. Decimals from recurring decimals. Sorry, from decimals going to fractions. That's how we can show that all decimals are all recurring decimals and terminating decimals are actually rational numbers. Let's move on. All right, here we go. 0,78 recurring as a fraction, show all working. So once again, yep, absolutely correct. We're going to let x equal to 0,78 recurring. And because there are 2 decimals over there, I'm going to multiply it first by 100 and then by 10. So 100x is equal to 78,8888 recurring. 10x is equal to 7,8888 recurring. And we've lined it up beautifully so that now we can subtract. Another thing that you'll notice is that I always put the big one on top. It just makes subtraction a lot easier. It eliminates error. So that's the way I like to do it. So here we have 90x is equal to 71. So x, which is what we were looking for, is 71 over 90. And that doesn't simplify. I'll prove it to you. 71 over 90. There we go. It doesn't simplify. So that is as it comes. All right. That's enough of these for the moment. Let's move on. Okay, here we're going to look at our estimation and also writing the numbers to 5 decimal places. So, a couple things. 5 decimal places and state whether they are irrational or rational. Okay, so what I'm going to do here is I'm going to rewrite all these and eventually use the calculator to get to 5 decimal places. And once I've done that, then we can state whether they're rational or irrational. Okay, now square root of 8, I could write as the square root of 4 times 2, which is 2 times root 2. I can't simplify 2 root 2 any further. That's absurd. That is irrational. So we use our calculator and we go 2 root 2 and we want the decimal places. 2,82842. 1, 2, 3, 4, 5. Have a look. The next number up is a 7. So this is going to have to increase by 1. And that is how we're going to write them correctly to 5 decimal places. So back to here, it's 2,82. Back to our calculator quickly. 843. 843. Now, I'm going to be absolutely technically correct and say that root 8 is not equal to that. It is approximately equal to that. We know that an irrational never ends. It's like Mr. Pi sitting in the corner. He just keeps going forever and ever and ever. So we can't really say that root 8 is equal to something because we'll never get to the last decimal place. Okay, now that's irrational. So let's just finish off this question quickly. And we can say that root 8 is an element of the irrationals. Right, let's have a look at the next one. Well, this over here is the same as 16 times 16 times 3. And we all know that 16 times 16 under the square root sign will just be 16. And root 3 can't go anywhere. So once again, that is irrational. Now, I know that not many of you know your 16 times table. So let's have a look how I would have done it on the calculator. Well, all I would have said was square root of 768, popped it, and we got 16 root 3. All right. In grade 8, you might have done rewriting surds in product of their primes. And then some primes could escape and some couldn't, and you had to do square roots and cube roots like that. Or, new days, we could just use the calculator if we have one. Right, let's see what this is actually equal to. 27,7128129. 1, 2, 3, 4, 5. Our sixth decimal place is a 2, means nothing is going to change. So 27,71. So that is approximately equal to 27,71. And get the last couple of decimal places, 281. 281. And we know then that the square root of 768 is also an element of the irrationals. Okay, there we have those two. Now, the next one, or the next couple, I'm going to rewrite as fractions. And then you see if you can spot if they're perfect squares, or if I'm doing cube roots, they're perfect cubes. That's one of the reasons why I told you perhaps you should memorize them. It's speed. We don't want to have to spend hours putting a finger on a calculator when we can just see the answer and write it down because we've taken the trouble to learn it. Some mental arithmetic sitting in the back of your brain is really advantageous. Let's have a look at the next one. Well, 0,49 is the same as 49 over 100. Aha! Is 49 a perfect square? Yes. Is 100 a perfect square? Absolutely yes. 7 over 10. So, 7 over 10, it's a fraction, an integer over an integer. Is it irrational? No. Is it rational? Absolutely yes. An integer over an integer, it's rational. So this one, 7 over 10, or the square root of 0,49 is an element of the rationals. Let's just write that up. So the square root of 0,49 is an element of the rational numbers. Likewise, in the next one, I'm going to go 16 over 10,000. The square root of that. Yep. Square root of 16 is 4. Square root of 10,000 is 100. Well, we know that we can write that as 1 over 25. Yes, once again, an integer over an integer gives us a rational number. So this one is also an element of the rationals. Quite easy, isn't it? Let's have a look at the last one that I'm going to tackle for you. The square root of 25 over 100. I can hear you screaming out the answer, 5 over 10, which, whoops, yes, can be simplified into a half, which is an element of the rationals. So, there we've done it. We've now converted square roots, things under square root signs, whether they are surds, we can classify them as surds, classify them as irrational numbers, or with a little bit of manipulation, see if they could perhaps be rational. So not every square root is going to be rational or irrational. You need to work on that. Let's have a look at the last question before we take another break. Well, looking at numbers, determine between which two consecutive integers. Remember consecutive? A number like perhaps 2, 3, 4, consecutive, one after each other. Between which two consecutive integers the following irrational numbers lie, without using a calculator. Ooh, not allowed to use our calculator here. So remember what we do. We remember our perfect squares if we're doing square roots, and our perfect cubes if we're doing cube roots. Right, let's have a look over here. Well, the square root of 4 would be equal to 2, and the square root of 9 would be equal to 3. Why did I bother with that? Well, we know that root 5 lies somewhere between root 4 and root 9. So 2 would be less than square root of 5, and also less than 3. So square root of 5 lies somewhere between 2 and 3 on our number line, our real number line. Let's have a look at the cube root of 5. Perfect cube time. Well, the cube root of 1 is 1. The cube root of 8 is 2. So the cube root of 5 has got to lie somewhere between those two. Writing up our answer, 1 is smaller than the cube root of 5, which is also smaller than 2. So, putting it in context, if we had 0, 1, 2, somewhere over there, somewhere along, we could have our cube root of 5. Just remember, we can't point specifically to the spot because it is irrational. We don't know its perfect value. But we can estimate really, really closely between which numbers it lies. All right, that encompasses everything that we need to worry about with numbers. And after a short break, we're going to look at number patterns. Not only linear number patterns, but a couple of really funky ones as well. Go stretch your legs and have a glass of water. I'll be with you in a few moments. Hi, welcome back. I hope you stretched your legs and had a glass of water, because here we're going for the second half of this section, which is called number patterns. Now, number patterns can be quite funky, and we're going to concentrate when we do the detail on linear number patterns. That means the first difference is the same. In other words, from one term, I'm going to add exactly the same number to get to the second, to get to the third, and to get to the fourth. We'll also touch on a couple of interesting ones like Fibonacci Sequence, and a couple of questions that they might even ask you if you're trying to go for Mensa. Anyway, here we go. Let's have a look at the first question that we've got up on our slide. You and 3 friends are studying for maths and are sitting together at a square table. That means there are 4 of you. A few minutes later, 2 other friends arrive and you move another table next to yours. Now 6 people can sit at the table. Another 2 friends also join your group, so you take a third table. And now 8 people can sit together. What they want to do is they want you to find the expression for the number of people seated at n tables. What is this thing about n tables? Well, n could be any number. 5 tables, 10 tables, 28 tables. You could be having a maths-a-thon and string 58 tables across your soccer field. What they want to know is how many people with how many tables. They want a formula. So when they want an expression, or they could say generalize, all they're wanting is a formula. Let's carry on. Use the general formula, there it comes up, to determine how many people can sit at 12 tables, and then how many tables are needed to seat 20 people. Well, here we go. Let's have a picture. There the first 4 people are sitting, 1, 2, 3, and 4. And then we add another table, so we've got 8 people in total. 1, 2, 3, 4, 5, 6. We don't have 8, we have 6. That was silly. We have 6. And then when we have 3 tables, we have a total of 8 people. So what we do is we make a table. Now, can I be very honest with you? making a table so that you can see the way the numbers go is vital. Whether it's an easy linear pattern or more complex, particularly next year and in matric, get into the habit of making up a table. Whip up a table quickly, see what the pattern is. You might have to do some calculations to get the formula, but always, always start with a table. Okay, here we go. 1 table, 4 people, 2 tables, 6 people, 3 tables, 8 people, and you can see here how it builds up. That's one way to do it, is to analyze the numbers and break down the numbers. And all that's happening is you're starting with a 4 and you're adding on 2 every time. Very obvious when you see it done for you. Slightly more tricky when you've got to do it for yourself. But we have a couple techniques to help you. Step 2 was to describe the pattern. Now that's the general formula. So 4 plus 2 into n minus 1. That there is our general formula. Our general formula where Tn is the number of people and n is the number of tables. There it's specified, n is the number of tables. So what we've done is we have now completed part A of the question. Part A was find a formula, and then they wanted to do 2 different things. One was to find the 12th term, and then we'll worry about the next one there. So here we go. Calculate the 12th term. In other words, if n is 12th. When they're talking about the term, that is your value for n. When they're talking about Tn, that is what's on the left-hand side. That's how many people can sit there in this instance, where n is the number of tables. So when you start with 1 table, 2 table, 3 table, 4 table, those are the values for n. Okay, and that's what your formula is constructed out of. So using the formula, all we do is we plug in the 12 and we get 26. What does that actually mean? That means 26 people can be seated at 12 tables. Now that's keeping T12 on the one side and putting 12 into the formula. Now what they're going to do now is they're going to give us the answer and we're going to have to find the n. They're going to give us the Tn and we have to go to find the n. Here it goes. Calculate the number of tables needed to seat 20 people. If Tn is 20, what is n? Well, there we write the formula. Tn was 20. There it is, 20. And all we've got to do is to use the form, is to work out the formula just like you would do in grade 8. Remember in grade 8, you had all those little equations that you battled with? Now you're grade 10. They're easy, absolute doddle. So this is where we're going to use that linear equation skill. Learned the skill, now we use it and implement it. So carrying on here, all we do is complete our equation and we get n is equal to 9. Now what does that mean? Remember, n is our number of tables, Tn was the number of people. N is the number of tables, Tn was the number of people. Let's move on to the next question. Very simple, very basic. We're going to start from basics. We're going to move on. Write down the next 3 terms in each of the following sequences. 5, 15, 25. I know that you can see that the difference between those two is 10, and the difference between those two is 10. What this is called is a first difference equation. The first differences are the same. Now, the only reason I mention it is that next year, maybe even this year if your teacher's extending you, you might do second difference equations. And then working it out like that is a really easy technique. Putting the little bits and working out the difference and writing it down. If you are trying to do AP Maths, try third and fourth difference equations. Exactly the same process, but quite technical. You've got to be very exact. I know that this one's easy. but all I'm doing is showing you a technique that will always work. Here we go. So 5, 10, 15, 25, my difference is 10, 35, 45, 55. What they want is 3 terms. We've given them 3 terms. Right, let's go on to part B, number B. 8 minus 3, 2. Well, my difference is 5. Minus 3, subtract negative 8 is 5. 2 subtract negative 3 is 5. First difference is 5. What is my difference? What is my D? My difference is 5. I'm adding 5 every time. So, here we go. We'll be 7, and 7 plus 5 will give us 12, and 12 plus 5 would give us 17, and that is how we would finish off that question. Last one here. Well, 30 to 27. My difference is going to be 3. In fact, I'm subtracting 3 as I move along. Once again, the first difference is the same. My D is negative 3. I'm going down by 3 every time. So, 24. Down by 3 gives me 21. Down by 3 gives me 18. Down by 3 gives me 15. And I've done my first 3 terms, my next 3 terms. Now, what I want to show you is something slightly different. Here's a sequence which goes 1, 1, 2, 3, 5, 8, and carries on. You can see that it's not a first difference equation. Something very, very different is happening. What I'm doing is I'm adding the first 2 terms to get the third term. Then I'm adding those 2 terms to get that term. Then I'm adding those 2 terms to get that term, and so on and so forth. This is an amazing sequence known as your Fibonacci sequence. Now, Fibonacci was an Italian mathematician. He had another name. He was known as Leonardo of Pisa. Now, Pisa is the town where you have that tower that is leaning, the Leaning Tower of Pisa. Leonardo, also known as Fibonacci, he lived there, and this was the sequence he did. Why is this sequence even interesting? Well, the ratio of consecutive terms eventually becomes the golden ratio. And if any of you want to study architecture, you'll know that if a building looks right, it is done in proportion to the golden ratio. You might like to go and investigate that a little bit. Wonderful, quite intricate. Many artists use the golden ratio to make sure that their paintings have an aesthetic appeal. They look right. Here's one last one I want to run by you. How about this one? 3, 3, 5, 4, 4. And it goes on. I actually gave this one to my grade 11s today, and I said, what's the next term? And they looked at me and said, but there's no real way. This doesn't actually work. You can't, there's no first difference, there's no second difference. It's not adding consecutive terms. So all I did was this. I wrote the word 1. I wrote the word 2. I wrote the word 3. Yep, you can see it. 4, 5. So what is the next number? Well, it's 3, because that's how many letters are in the word 6. That's a cute one, isn't it? Maybe you and your buddies would like to experiment and try different patterns. That one also comes out of one of the Mensa tests, if you can see things slightly differently. You won't get something like that in an assessment, but it's a lot of fun to try and do things like that. Okay, let's go back to what we're really supposed to be doing. The general term is given for each sequence below. Calculate the missing terms. Now here's a general term. It's actually a quadratic. It's got a squared in it. And we're given term 1 and we're given term 2, and we've got to work out what is term 3. Well, given a formula, all I have to do is to replace my n with a 3. And in this case, I land up with 8. So my missing term is 8. Just to reiterate, yes, the answer was 8. Just to reiterate, it's not linear. In other words, the differences between consecutive terms are not the same. If you want to have a challenge for yourself, have a look at the second differences. You'll see they are the same. Let's move on to 2b. Here we're given our general formula, and we've got the 1, 2, 3, 4. We have to find the fifth term. In other words, n is 5. So all we do is replace n with a 5, and in this case, we've got minus 1. So our missing term was minus 1. Now, that over there is an n to the power 1. So let's have a look. The difference is 1. The difference is 1. The difference is 1. Yes, it's linear. The first differences are the same. Now, you don't have to use the general formula in this question, 3, 2, 1, 0. Oh, please, primary school kid could get this one. But perhaps it was slightly more difficult. I'm just showing you a technique on how to get the answers. Let's do the next one. Here we have to find T2 and T4. So there are 2 bits we have to do. So T2 is minus 13 plus 2 times 2, which gives us minus 9. So T2 is minus 9. And yes, you can probably see what's happening. It's going down by 2. If we were to change color ink, that will be increasing by 2. That will be increasing by 2. And if we were to do it this way, increase it by 2, we should get an answer of minus 5. Well, let's check. Does T4 give us minus 5? Well, minus 13 plus 2 times 4 gives us minus 5. So we were correct. So there we go. What I've done is I've used the general formula, and I've also used common sense. Please, always look at the question, use a bit of common sense. Perhaps by inspection, you can get the answer a lot quicker than going through the elaborate process of doing the formula. Let's move on. Find the general formula. Right. Here we go. Find the general formula. Now, for linear, T equals A plus N minus 1D. Tn equals A plus N minus 1D. I'm going to write it down, and what I really expect you to do is put on a piece of paper and pop it somewhere that you'll be able to memorize it quite quickly. With that, linear general formulas are at your footstep. Here we go. Tn is equal to A plus N minus 1D. Right, you might be asking, what does A stand for? A stands for our first term. And D is this difference I've been talking about. This is for linear, where the first differences are the same. So what we're going to do is we're going to check over here on the screen in a few seconds, is this a linear general formula? Here we go. Well, 2 to 5 is 3, 5 to 8 is 3, 8 to 11 is 3, 11 to 14 is 3. Yes, it is a linear equation. So, Tn is equal to A plus N minus 1D. Our A value is 2. Our first value is 2. Our D is 3. So that was our A, and that over there was our D. And all I'm going to do is pop it into the equation. Tn is equal to 2 plus N minus 1 times 3. Now, all I'm going to do is I'm going to make this look pretty. So I've got the Tn is equal to 3n minus 1. Now, that's how I would work it out. What they're asking us to do now is they're asking us to find T10, T50, and T100. So all we've got to do is find the 10th, 50th, and 100th term. Now, I can hear someone in the back of the class saying, but you could count and write out 2, 5, 8, 11, 14, 17, and keep going till you get to the 100th term, and then write down your answer. You don't need formulas. Fair enough. That's one way to do it. How long is that going to take? Are you going to be able to do all the work that's necessary in your assessment? I think not. That's why we use general formula. They save time. Right, let's answer the questions quickly. They asked us for T10, so T10 will be 3 times 10 minus 1, which will be 29. They ask us for T50. So that'll be 3 times 50 minus 1, which will be 149. They ask us for T100. T100 will be 3 times 100 minus 1, which is 299. And there our 3 answers are. That was not too difficult, was it? Difficult part is finding the formula. Right, let's do another one. Right, here we go. 0 to 4 is 4, 4 to 8 is 4, 8 to 12 is 4. We know that A is equal to 0 and D is equal to 4. Quite straightforward. Let's put it into our formula. Tn is equal to A plus n minus 1d. Yep. 0 plus n minus 1. That should be an n over there. That should be an n minus 1 times 4, which is 4n minus 4. So answering the questions, what were the numbers they wanted us to do? 10, 50, and 100. So T10 is 4 times 10 minus 4, which is 36. T50 will be 4 times 50 minus 4, which will be 196. And T100 will be 4 times 100 minus 4, which will be 396. General formula. Linear general formula, quite easy. I'm sure you're happy. What we're going to do now is go and put these into context. We're going to have a word problem around it, and we're going to have to extract the information into our table so that we can get our sequence, our 0, 4, 8, 12, or whatever. Here we go. The seating of a sports stadium is arranged so that the first row has 15. Haha. I'm going to start my table straight away. My first row has 15. My second row has 19. And my third row has 23. Right, I've done that vertically. Let's put the numbers horizontally and see if there pops up to give us anything that we can use. Well, from 15 to 19 is 4. From 19 to 23 is 4. That's a general formula, a general linear formula. How many seats in the 25th row? They're looking for T25. Okay, you can count in 4s from 15 upwards, or we can write our general formula. Tn is equal to A. A was 15 plus n minus 1 times D. We've got D is equal to 4. Our general formula, 15 plus 4n minus 4, which is 4n plus 11. There's our general formula. Now let's answer the question. They wanted T25. All right, so T25 will be 4 times 25 plus 11, which gives most of us 100 and 11. Well, not enough seats if Chiefs are playing Pirates, but anyway. What I want to reiterate is just how important it is to start off with your table. If you do your table, you can write out your sequence, find out, is it going to be linear? Is it going to be quadratic? Is there something funky going on that you can't really see? Get a general formula, then answer the question. Quite a nice one. Let's do another one. A single square is made from 4 matchsticks. Well, a single square. 2 squares in a row need 7 matchsticks. How does that work? Well, we're going to add on another 3. And 3 squares in a row need 10 matchsticks. All right, so the first term. Let's leave that for a moment. We've got 4, we've got 7, we've got 10. Is it going to be linear? Well, that's adding 3 and that's adding 3. So yes, it's going to be linear. First term is 4. Common difference is 3. No money for guessing what C is. General formula. So Tn is equal to A plus n minus 1 times D, and tidying that up like a good student, 3n plus 1. There's my general formula. They've now drawn a diagram for us. How many matchsticks in a row of 25 squares? So they are looking for T25. So, keeping in mind our general formula, which we worked hard to calculate over there, we've got 3 times 25 plus 1, which is 76. What does that mean? That means you've got 76 matches. You can make 25 squares in a row. Remember, the n is the number of squares, and the Tn is the number of matchsticks. Let's move on. Right, this is the last question we're going to handle today. And once again, all we're going to do is to read it through carefully, put our numbers down, make a table, generalize, answer questions. Okay, here we go. You would like to start saving some money. Fantastic idea, by the way. But because you've never tried, you decide to start slowly. At the end of the first week, it's 5 Rand. So first term is 5 Rand. At the second week, you deposit 10 Rand. And the third week, it's 15 Rand. After how many weeks will you deposit 50 Rand into your bank account? That's the question that they're going to be asking us. We now need to put down our numbers and make some sense of it. Well, 5, 10, 15, yep, you said it and you saw it. It's first difference. I'm going to go through the process of working out a general formula and then working out after how many weeks it happens. In a case of 50, this 50 Rand, you could do it manually and count up. We'll do that as well in a few seconds' time. Hang in there. Let's do it the formal way. Remember, what I'm trying to teach you is a process that will always work. Here we go. So Tn is equal to A, our first term was 5, plus n minus 1 times our difference, which was 5 as well. So it's 5n. What they want is 50 Rand. The 50 Rand is here. We have to find the n. Is equal to 5n. So n is equal to 10 weeks. Yep, that one was really easy. Let's just try it that other way. Well, if we had 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th week. Yes, it would have worked like that as well. Just be careful of those numbers. I remember years ago I had a child who went to the 100th term and actually he messed it up. And it wasted a lot of time. But anyway, it was good for a laugh. What I'm going to do is I'm just going to summarize and bring a couple of things together. In the first half, we looked at rational numbers being fractions and irrational numbers being our non-terminating, non-recurring decimals. And we know that our rationals together with our irrationals make up our real number system. What we also looked at is at recurring decimals. 0.7 recurring is the same as 7/9. 0.82 recurring is 82/99. And what we also looked at was an elaborate way of proving that that was the right fraction. Proving that recurring decimals belong with the rationals. Just something interesting. We know that 0.7 recurring is 7/9, and 0.8 recurring is 8/9, and 0.9 recurring is 1. Point of order, it is 1. Not it is almost 1, it is 1. There's also a lot of rubbish written about it on the internet, but you find some reputable sites and they will say that 0.9 recurring is 1. Okay, what else did we do? We looked at surds. Where would root 2 be placed on our number line? On our number line, 1, 2, 3, where would root 2 be placed? And then we went on and we looked at number patterns, and the biggest thing we had to remember was Tn is equal to A plus n minus 1 d. We looked for the differences between our terms, and we looked for our differences and to see, first of all, is it linear, and then to get a general formula. Right, that's all we have time for, and I hope you've had a good time. I hope you've learnt a lot. Anyway, all the best for the rest of grade 10. Thank you.